Hi students, I welcome you all for this video lectures. In the previous lecture we will see about the types of crystal system part 2, the classifications of crystal system based on their internal molecular force such as ionic, covalent, metallic and molecular crystals. The classifications based on their internal structural arrangements of atoms such as metallic crystal structures, ceramic crystal structures, and finally we will see about the polymer structures. In this video lectures we are going to see about the 14 types of Bravais lattice and Miller indices. Before going into the topic, we will see about the introductions of Bravais lattice. In 1880, Bravais introduced the idea of space lattice. According to this theory, there are only 14 types of possible arrangements of lattice points in a space in which each point is identical to all other points in it. Hence, there are the only 14 space lattice which can be developed from the 7 crystal systems. These 14 types of space lattice are said to be Bravais lattice. This table can explain the 14 types of Bravais lattice which can be developed from the 7 crystal systems. The first crystal system is the triclinic crystal systems which contains 1 Bravais lattice. Then the second system it is a monoclinic system which contains 2 Bravais lattice. Then the third one orthorhombic contains 4 Bravais lattice. Then the tetragonal contains 2 Bravais lattice. Hexagonal and orthorhombic each contains 1 Bravais lattice. Finally, the cubic system consists of 3 Bravais lattice. Hence, the 14 Bravais lattice can be developed from these 7 crystal systems. We will see in detail about these 14 types of Bravais lattice. First, we will discuss about the triclinic Bravais lattice. In these crystal systems, there exists only one type of Bravais lattice, which is a primitive cell. It obeys the following lattice parameter relationship, that is A is not equal to B, B is not equal to C, and alpha is not equal to beta, beta is not equal to gamma, that is not equal to 90 degree. The figure illustrates the triclinic Bravais lattice in which each atoms are located at the corner of the systems, that is the primitive cell. The second one is the monoclinic Bravais lattice. In these crystal systems, there exists 2 types of Bravais lattice which are primitive and base center systems. It obeys the following lattice parameter relationship, that is A is not equal to B, B is not equal to C, and alpha is equal to gamma is equal to 90 degree, which is not equal to beta. The figure illustrates the Bravais lattice of monoclinic crystal system which consists of 2, that is the primitive cell in which the atoms are arranged at the 8 corner of the unit cell. Then the second one is base center in which the atoms are arranged at the corner of the unit cells and also at the 2 faces of the unit cell, that is top and bottom faces. We will see about the orthorhombic Bravais lattice. In these crystal systems, there exist 4 types of Bravais lattice which are primitive, body center, face center and phase center systems. It obeys the following lattice parameter relationship, that is A is not equal to B, B is not equal to C, and alpha is equal to beta, beta is equal to gamma, which is equal to 90 degree. The figure illustrates the 4 types of Bravais lattice which of the orthorhombic crystal system. The first one is primitive in which the atoms are arranged at the 8 corner of the unit cell. The second one is base center orthorhombic crystal systems in which the atoms are arranged at the bases of the unit cell and at the 8 corner of the unit cell. Then the third one is nothing but base center orthorhombic Bravais lattice in which the atoms are arranged at the 2 faces of the unit cell along with the 8 corners. And finally, the fourth one, which is nothing but phase center orthorhombic Bravais lattice in which the atoms are arranged at the 8 corners along with the 6 faces of the unit cell. Next, we are going to see about the tetragonal Bravais lattice. In this crystal system, there exist 2 types of Bravais lattice which are primitive and body center tetragonal crystal systems. It obeys the following lattice parameter relationships, that are A is equal to B, which is not equal to C, and alpha is equal to beta, and it is equal to the gamma, which is equal to 90 degree. The figure represents the 2 Bravais lattice for the tetragonal crystal system. First one is a simple tetragonal or primitive cells which contains the atoms at the 8 corner of the unit cells. The second one is the body center tetragonal crystal systems in which the atoms are arranged at the 8 corner of the unit cells and at the center of the unit cell. Next, we are going to see about the hexagonal Bravais lattice. In these crystal systems, there exists only one Bravais lattice which is nothing but a simple cell. It obeys the following lattice parameter relationship, that is A is equal to B, which is not equal to C, and alpha is equal to beta is equal to 90 degree and gamma is equal to 120 degree. The figure represents the hexagonal Bravais lattice in which the atoms are arranged at the 8 corner of the unit cells which are shaded in a blue color. Next we are going to see about the orthorhombic Bravais lattice. In these crystal systems there exists only one type of Bravais lattice, which is a primitive cells. It obeys the following lattice parameter relationship, that is A is equal to B, B is equal to C, and alpha is equal to beta is equal to gamma, which is equal to 90 degree. The figure represents the orthorhombic Bravais lattice, in which the atoms are arranged only at the 8th corner of the unit cell. Next we are going to see about the final cubic Bravais lattice. In these crystal systems there exist here 3 types of Bravais lattice, which are primitive, phase center and body center cubic systems. It obeys the following lattice parameter relationships, that is A is equal to B, B is equal to C, and alpha is equal to beta is equal to gamma, which is equal to 90 degree. The figure represents the 3 Bravais lattice for the cubic system. In the first simple cubic systems, the atoms are arranged at the 8th corner of the unit cells. The second one is phase center Bravais lattice. In these systems, the atoms are arranged at the 8th corner of the unit cells and at the 6 faces of the unit cells. The third one is body center cubic systems. In this system, the atoms are arranged at the 8th corner of the unit cells and one atom at the center of the unit cell. Next we are going to see about the Miller indices. Before going into the topic, we will discuss what is the need for this Miller indices. The physical properties of the crystals are depend upon the number of atoms at the planes. The orientation of the planes can be represented by the intercept of the crystal planes with 3 crystallographic axes. In the figure, the crystal is drawn which the planes cuts the 3 crystallographic axes, 1 unit in the x-axis, 3 unit in the y-axis and 1 unit in the z-axis. Then the intercepts can be called as 1, 3, 1. The Miller suggests a better way to represent these crystal planes in the crystals, which are called as Miller indices. Next we are going to see about the procedure for finding these Miller indices of the plane. First point is to find the intercept of the plane with the lattice constant. For this example, it is 1, 3, 1. Then second point is take the reciprocal of this intercept. For this example, it is 1 by 1, 1 by 3, 1 by 1. Then the fourth one is take this reciprocal into a whole number by multiplying each with the LCM. For this example, it is 3, 1, 3. Then fourth point is that the final point, that is called as we reduce this with a square bracket. The number is enclosed with this square bracket, that is nothing but 3, 1, 3 for this example. The fourth point is the enclose these numbers using the square bracket. For this example, the Miller indices is 3, 1, 3. Next we are going to see some of the example to find the Miller indices of the crystal plane. First one, here the plane is given which is parallel to y and z axis. Then the intercept of this plane is given by 1, infinitive, infinitive. Then next we are taking the reciprocal of this intercept. Then the values are 1 by 1, 1 by infinitive, 1 by infinitive. Then we reduce this reciprocal into a whole number, that is 1, 0, 0. Then the Miller indices of the plane is given by 1, 0, 0. Next, in this example, a plane is drawn which cuts x-axis and y-axis and it is parallel to z-axis, and the intercept of this plane is 1, 1, infinitive, and the reciprocal of this plane is 1 by 1, 1 by 1, 1 by infinitive. Then we reduce this reciprocal into the whole number, that is given by 1, 1, 0. Then the Miller indices of the plane is given by 1, 1, 0. Next we are going to see about the important feature of the Miller indices. These Miller indices describe the angular position of the plane with respect to the 3 crystallographic axes, that is x, y, z. But it does not describe the actual distance from the origin. All equally spaced parallel planes have a same Miller indices. That is, hence the Miller indices does not describe the angular position of a single plane but for a set of planes. When these planes are parallel to any one of the axes, then we can say that it meets that axis at the infinitive. That is, the length of that intercept is infinitive. It is only the ratio of Miller indices are important. That is, the plane with the Miller indices 8, 4, 2 and 4, 2, 1 are represented the same set of Miller indices. A negative index indicates that the plane cuts the axis at the negative side of the plane with respect to the origin. Now we will see the procedure for drawing the crystal planes. Following are the procedure to draw the crystal planes using the Miller indices. Take the reciprocal of the Miller indices. If the Miller indices are HKL, then the reciprocal of the Miller indices are 1 by H, 1 by K, 1 by L. Then this reciprocal will give the intercept of the crystal planes. These intercepts are marked in the unit cell, and finally a plane is drawn. Now we will see few examples. Draw the crystal plane where the Miller indices are 1, 1, 0. Take the reciprocal of the Miller indices. If the given Miller indices is 1, 1, 0, the reciprocal of the Miller indices are 1 by 1, 1 by 1, 1 by infinitive. Then the intercept of the crystal planes are 1, 1, infinitive. If any axis have the intercept is infinitive, then we must draw the plane which is parallel to that axis. Then these intercepts are marked in the unit cells and the plane is drawn, which is shown in this figure. It cuts the x and y axis at one unit, which is parallel to z axis, where the intercept of the z axis is infinitive. We will see another example. Draw the crystal plane where the Miller indices is 1, 1, 1. Take the reciprocal of the Miller indices. The given Miller indices is 1, 1, 1, and the reciprocal of the Miller indices is 1 by 1, 1 by 1, 1 by 1. Then the intercept of this crystal plane is 1, 1, 1. Then these intercepts are marked in the unit cell, and finally a plane is drawn in the unit cell, which is shown in this figure, which cuts the x, y, z axis at one unit each. Let us come to the end of the session. I hope you have understood about the 14 types of Bravais lattice and the concept of Miller indices. In the next session, we will going to discuss about the characterization of unit cells. Thank you.